and let's move on. So our next speaker is Anya Feldman. Welcome, Anya. And Anya got her PhD from CMU. Then next 4 years, she worked at AT&T Lab Research before taking on professor's positions in Europe, Starland University, TU Munich, and then TU Berlin. In May 2012, she was elected the first woman on the employer side of the supervisory board of SAP, a great accomplishment. And then since the beginning of 2018, she is the director of the Max Planck Institute for Informatics in Saarbrücken, Germany. And she's a member of the German Academy of Sciences, the BBAW, and Academic. So welcome, Anya, and look forward to your talk.
Thank you very much for this nice introduction. And today I want to talk about P4 as two sides of the same coin. So what do I mean by it? Well, P4 has many strengths, and we already saw some of that in Jennifer's talk and in some of the other talks in the past few days, where it's all about the ability to gather fine-grained network information in order to do network telemetry. On the other hand, whenever we introduce programming into the network or in any parts, there are new chances for novel bugs, meaning we need new software abstractions. And I basically want to use this talk to give you two examples of two projects that we are doing, one on the strength side and one on the weakness side. So let's get started. Network telemetry. And what I want to talk about is P4-enabled network-assisted congestion feedback. What do I mean by that? Well, if we're looking at today's routers, today's switches, one of the things that we have to look at are such things as buffers, the characteristics of the switches, as well as the network traffic. What do we observe there? Well, buffers are getting shallower, at least relative to the link speed. And of course, they should be shallow because we all want deterministic delays. We don't want to have runtime times that are growing up to seconds because of buffer bloat. And of course, with today's switches, just as we heard a moment ago, we have the ability to actually gather fine-grained statistics. And we can use multiple different queues. But why do we need those multiple queues? Why should we need fine-grained statistics? Well, if you look at traffic, there are so-called mices and elephants. Mices are the ones that actually don't contribute a whole lot of traffic. Elephants are the ones that are the big guys. Those actually contribute most traffic. Now, why do we care about mice and the elephants in the sense of congestion control? Well, the elephants, the ones that contribute most of the traffic, they can actually react to congestion signals. The mice, on the other hand, they are not subject to congestion control. So if you have lots and lots of mice, they will just come in and bam the network with all the traffic, which is part of the problems of SYN attacks and other kinds of attacks. They are not subject to congestion control. So wouldn't it be nice to actually separate those mice from the elephants so that the mice can actually not interfere with the elephants and let the elephants move on? And at the same time, of course, you do need some amount of bandwidth for the mice because otherwise the elephants may just stamp on the mice, which the mice probably won't like either. So what about congestion inference? At the moment, it is still left mainly to the end system. So if we're looking at it, we have a source over here, we have a destination over here. What do we see? Well, we can do it implicitly via delay and loss, which is what TCP currently does. Or we can do it a little bit more explicitly via TCP ECN or rate control of some kind, but then we still have to go between the source and the destination. Now, of course, you could do policing, or you could do back pressure if this is your router that is actually congested, or you could send choke packets. Now, this is what we have today. These are the ones that were kind of said, no, not a good idea. but things that were once introduced were probably introduced because of good reasons. And we should revisit these every so often. And indeed, we think that the basic idea of having the network inform the sources in terms of, hey, there is congestion control inside the network. With the new capabilities of P4, this should be feasible again. So why not actually do it network assisted? In the sense that if we have a router that is actually suffering from congestion, it should be able to notify the source, hey, you guys better slow down. Now, what are the insights? Well, we can actually take advantage of P4, and with that, we can indeed generate NACs at high speed if needed, but also make sure that we're not sending too many of them. And indeed, we can use the concept of packet trimming in the data plane and then reflect the packet back as a NAC back to the source. Moreover, we can actually identify elephants and mice using network telemetry and separate them into different queues so that we can have one kind of a control queue for our NACs, an elephant queue and a mice queue, based on some kind of statistics here. Now, based on that, we can actually have a more informed TCP congestion control, which actually knows where in the network the congestion is, how far away it is, and how much congestion there is. And that can be then used in order to slow down the senders so that everybody inside the network can achieve better throughput. How can we identify those mice and elephants and also identify sources that we may want to slow down? Well, we can use rolling sketches. We can have multiple different time windows and basically have counters per flow, much in a similar way as Jen was just talking about. These can generate rolling counters based on sketches, and this is where all the new concepts that have been introduced in the various different networking conferences can be put together, and we can take advantage of the programmability of the network switches. So, what are the advantages of NCM? The core idea is to provide fast and direct feedback directly to the source. Now, some people may say, but wait a moment, we don't want this because this is leaking information. Or how do I know that this information is indeed valid? Well, you may want to do it only for part of the network, the part that you actually trust. Or you might want to say, wait a moment, I can actually infer if the packet was lost in the end. I don't have to necessarily trust this. And if I identify elements in the network that are cheating, I can actually ignore the NCF signals at the source. We can do separation of mice and elephants. And indeed, we could do very flexible allocation of buffer memory between the elephants and the mice. What is the status of the project? We have prototype implementations, both in P4, on Tofino switches, as well as in NS3, and the results look fairly promising. So that was the one side of the coin. Now I want to talk about some of the challenges that we also have to address when we're introducing new capabilities such as P4. And that is, we need to think about verifying P4 programs, not just via static analysis, but also at runtime. Why is that? Well, one of the things is certain bugs only occur once you have various different input workloads, because you don't really think about some of the things that could go wrong while you're programming your P4 elements. Also, you're programming P4, but some of the elements of the P4 switch, such as the match action table, they are actually being populated via the networking content. So you may not be aware of all the input in order to do your verification statically. Also, there are platform-dependent bugs that really depend on the platform that you're looking at. And as such, we claim that you do need runtime verification in order to check if your switch or network behavior is indeed the one that you want. How do we propose to do this? Or what is the challenge that we need to address? Well, P4 is a partial program. Routes are populated at runtime, and P4 does not have runtime exceptions. So bugs are hard to localize. Static analysis is not sufficient. We do need more in order to detect runtime bugs. One of these examples is the one being demonstrated over here. We have a user, we have a P4 switch, and this P4 switch may actually kind of do the update of the IP checksum, but if it doesn't, or check, for example, if there are IP options available, the adversary may be able to send certain mainframe form packets that are still going to be forwarded to the server instead of somewhere else, or that may be dropped unnecessarily. If you're interested in more scenarios, there is an Infocom paper that just appeared that actually contains all of these examples. So, how do we want to do this? Well, first of all, we of course need to understand what is the expected behavior. And we can get that via static analysis. We are looking at the forwarding routes. We are actually augmenting the code with test cases, what should be checked for. Once we have that, we can take our P4 switch over here, and we can actually subject it to various different test packets. How to do that? Well, let's use a fuzzer, because fuzzing is a really successful element in which you can actually test the runtime behavior. Now that fuzzer, of course, needs to kind of check, did it actually do what it was expected to do or not? And then we can actually use a reinforcement-based learning agent to kind of use feedback whether the packet was forwarded the way it was supposed to do in order to kind of reward it, in order to enhance its capability to do the bug detection as quickly as possible. Once we have that, we can see, can we actually localize in the P4 code which part of the code may be actually responsible for it? And once we have that, we can even think about, can we patch the behavior if we have certain patches available that have been used in the past and that have been proven successful. And once we have that, we can update the program, upload it to the P4 switch again, and continue on the fuzzing. Now, does this work for all kinds of different P4 programs? Probably not. But one of the advantages that we have at the moment is that P4 is a very simple language. The code is fairly simple, and as such, we can hope to actually benefit from joint activities over here, to have patches ready, to be able to actually localize where the bug may be, and in order to actually fix it, so that we don't repeat bugs that have been detected in the past. So we tested this on 8 of the public P4 programs that are out there. We actually have various different baselines, and we did find about 10 different bugs with this project, and it's been quite successful as such. So I wanted to talk about in this keynote about 2 sides of the same coin. The fact that we have lots of new challenges that we need to do, but we also have lots of new abilities in terms of verifying the programmable switches, not just at compile time, but also at runtime. At the same time, we can capture all of these new network telemetry data, and we can use detailed feedback from the network, which includes such things such as queue length that is currently occupied, the number of element flows, the number of mice flows that can be sent back to the sources, for example, using TCP options, and as such enhance TCP congestion control. And with that, I'm very happy to take questions that you may have. Thank you very much. And I also want to thank all my collaborators that made all of this work possible. Thank you.
Anya, thanks so much for a very nice talk and some of the insights, and especially the what you call the 2 sides of the same coin. So highlighting some of the limitations with the P4 and the P4 environment. So I guess just trying to understand, and again, I don't have that much sophistication or depth in this. So I'm trying to understand if you see the P4 language and the toolchain itself maturing in order to deal with some of this, or all of this has to be done in the runtime?
So I have to admit, I'm not 100% an expert on all the program verification strategies that are out there. I think you can do a lot using static analysis, and there have been so many different successes in terms of improving this. Nevertheless, purely because you have some platform dependencies, you cannot do everything statically.
No, mm-hmm.
And the other thing why you cannot do everything statically is because you have an interaction between the program that you compiled and then the match action tables that are populated via the input data that you have. And that input data that comes from this packets, you don't really know. And those are the kinds of edges that you will have to test using runtime verification. And you cannot do purely statically.
No, so I agree that you cannot get away with only static. So that is, I agree. I was just asking whether on the static front, are there things that you see we can do more? And then of course, on the, my second question is going to be on the runtime side that you, anyway, but okay.
I think one of the things is P4 is a very low level language at this point. It would be really nice to have higher level abstractions. And there are ongoing works, and I think there will, for example, be a SICOM paper appearing that will be covering more high-level abstractions than P4 for programming such switches as the Tofino ones, because P4 is very much low-level programming. It's more C-like, or it is very much C-like, and would be really nice to move this up to a higher level abstractions in terms of the programming concepts, because there's so much certain things that you should never do, but you can certainly do with P4.
And I was also thinking about, as far as the runtime thing, is there a particular roadmap that you will think is what, I mean, what you are pursuing and what the community can pursue, and what would that look like?
Let me put it this way. I think it would be really good to have some kind of way that we can annotate the P4 programs in terms of their expected behavior so that we can check things against it. And it would be nice to have a language for that that actually captures all the various different needs. It would also be very nice if we can have some standardized test cases that we should actually set any kind of a P4 program to make sure that certain basic things just don't happen. And as such, having a fodder there may be very, very useful. And we have to see how this all evolves, but it would be great if some of these concepts that we have been introducing here would be taken over by those network operators that actually want to deploy P4 programs within their networks.
But are these concepts can be packaged into some kind of tools or something that the community as a whole can use, or is this something that is very, go ahead?
Yes, I do think so. That so we have some initial tools, and Approve has been the main driver of it. And I think some of this is indeed open source. And if there's anybody interested, please contact me so that we can actually see how we can move forward on this.
So with that, Anya, again, thank you so much. Really appreciate it. And we'll move on to the next speaker then. Thank you again.
Thank you.